Yes, hello everyone, welcome on YourPedia platform. I hope you all are fine and your GATE preparation is going very well. So guys, again I am here in front of you with one NPTEL assignment question. As you all know, we have launched this particular series last year and this year also we are continuing with that NPTEL assignment question. So guys, today I picked one question from the chapter 3.1 conduction. Okay, this question I picked from subject heat transfer from the topic heat generation. Okay, so in some kind of cylinder or in some kind of tube if you are having, and if there is some kind of heat is generating, then how to solve such kind of problem, that we are going to discuss. Okay, so very typical gate level problem is there in that assignment, NPTEL assignment, and earlier also similar kind of questions were asked in GATE examination if you check. So guys, let us move to the question. So this is a question we are going to discuss. Radioactive waste which is having conductivity 20 watt per meter Kelvin. There is only slight difference, but similar kind of question you will find in the GATE previous year examination also. So very good question, and student generally they face difficulty in solving such kind of question. That's why I picked this. So there is a radioactive waste is stored in a cylindrical steel shell. So there is a cylindrical steel shell. In that radioactive waste is stored. The conductivity of the radioactive waste is 20 watt per meter Kelvin. The conductivity of the stainless steel is 15 watt per meter Kelvin with the inner and outer diameter this. So the stainless steel shell inner and outer diameters are given to us. Thermal energies is generating uniformly within the waste material at a volumetric rate. So heat generation per unit volume is given to us, which generally we represent by Q dot G, volumetric heat generation. So watt per meter cube, how much is the heat is generating, that is given to us 2 into 10 to the power 5 watt per meter cube. The outer container surface is exposed to water. So the entire arrangement, the stainless steel shell is immersed in some water. Is a kind of realistic case, because in real also in nuclear power plant the entire arrangement, the radioactive material is filled in some stainless steel shell we filled, and the entire arrangement we immerse in water only just to transfer the heat. So here also similar kind of thing is happening. The outer container is exposed to water at 25 degrees Celsius with a surface heat transfer coefficient of 1000 watt per meter square Kelvin. So as you can check from the unit only, so this is what convection heat transfer coefficient, H value outside is given 1000 watt per meter square Kelvin. The ends of the cylindrical assembly are insulated. This is very important point, guys. The ends are insulated. So this is a kind of cylindrical steel shell. The ends are insulated. It means what? He is indirectly telling you, you can go with one directional radial heat transfer, guys. So there is no heat transfer in the longitudinal direction because the ends are insulated. So there is no heat transfer in that longitudinal direction. So very accurately you can go with one dimensional radial heat conduction. Okay, so this is the meaning of this particular line. So that all heat transfer occur in radial direction. He mentioned also, just to give you clear idea, he mentioned also very clearly heat transfer is in the radial direction only. For this situation, the steady state temperature, one more thing guys, the entire arrangement is in steady state. Okay, so he is asking you the central line temperature of the waste material, TO. TOTC you can represent. I am going to represent it by TO, central line temperature of the waste material. So guys, there is only one change. Normally when we get such kind of question, we have a material in which some heat is generating and the material is exposed to the surrounding, but here the material is covered by some stainless steel shell and then the arrangement is is in contact with some water at 25 degrees Celsius. So if I draw the diagram, it is something like this. So there is some radioactive material first, something like this. Okay, this radioactive material is filled in the inner shell. This is filled in the inner shell, obviously the inner part of the hollow stainless steel. So this is the diameter is 1 meter. इसका diameter कितना है बच्चों? 1 meter. Okay, so this is enclosed in a stainless steel shell. So something like this. So this is a stainless steel shell, something like this. You can represent. So let me represent it like this. Okay, something like this. So this is stainless steel shell. Okay, and the outer diameter of this stainless steel shell, the inner diameter is 1 meter, the outer diameter of the stainless steel shell is given to us 1.2 meter. So this is 1.2 meter. Okay, so this data he has provided us. Let me write some more things, guys. So this is radioactive material. The conductivity of this is also known to us. The conductivity of stainless steel also is known to us. Let me write both. This is the conductivity of radioactive material and the conductivity of radioactive material is this. he has given us 20 and the stainless steel it is 15. So this is 20 watt per meter Kelvin and this is 15 watt per meter Kelvin. Okay, so let me write it here, 15 watt per meter Kelvin. So the entire arrangement is exposed to water. So water T infinity, the temperature is 25 degrees Celsius with the convection heat transfer coefficient 1000 watt per meter square Kelvin. Let me check the data. So convection heat transfer coefficient is given to us 1000 and the water temperature is 25 degree Celsius. Okay, and the heat which is generating in the radioactive waste material is what? 2 into 10 to the power 5 watt per meter cube. So this entire data is given to us. So at what rate heat is generating, guys? In this material the heat is generating uniformly heat is generating at this rate, 2 into 10 to the power 5 watt per meter cube. So these all informations are given to us, guys. And what he is asking, guys, he is asking you to find out the central line temperature of the radioactive waste material. So this particular temperature, guys, this particular temperature, and I am representing it by TO. So this temperature you need to find out. So this is the entire problem, guys. Now, because the entire arrangement is in steady state, you know, there is no accumulation of energy is going to take place. Steady state means there is no accumulation. The properties of the system are not going to change with the time. So whatever heat is generating, that is going to conduct and that only is going to convect out of the material. So in steady state, you can write it here, the total heat which is getting generated, that is equal to heat which is going to conduct through the material and that is equal to heat which is going to convect through the material, guys, convect out of the material. Okay, so if you equate, because here this is the central line temperature TO, okay, and suppose this temperature is what? TW. This temperature is TW, wall temperature. So this is TO, this is TW, wall temperature. Okay, and then this temperature we don't know, guys. This temperature, even we don't know TW also. But suppose if you are able to find out this, then you can easily obtain this TO. There is a very basic relationship between TO and TW. I'm going to drive that in front of you. So if you know this TW, then you can easily get TO, guys. But this TW is also not known to us. But that you can easily find out by equating what? This Q generation. Q generation is nothing but 2 into 10 to the power 5. This is the volumetric heat generation. Multiply by volume of the radioactive waste material, which is nothing but pi by 4 d square. So the diameter of the radioactive waste material is 1. So pi by 4 1 square. This is the area into what? Length. Suppose length is L. Okay, length is not given. So pi by 4 d square into L. This is the heat which is getting generated. Yes or no? So this, if you equate it with what? The temperature difference TW minus T infinity. TW minus T infinity. T infinity is 25 degrees Celsius. So T infinity, which is nothing but 25 degrees Celsius, divide by, and guys, if you are taking this and this temperature, then how many resistances are there between this and this temperature? There are two resistances. It's a combined case. A combined case of what? Conduction plus convection. So here the conduction is going to take place and here the convection is going to take place. So it is a combined case. Okay. So TW minus T infinity divided by total resistance, summation of all the resistances, and that will be what? Ln of R2 divided by R1. So R2 is 0.6. R1 is what? R1 is 0.1, 0.5. So here if you take this distance, so this is R2, this is R1. So this temperature is TW. So ln of R2 by R1, so this will be ln of 0.6 divided by 0.15 divided by 2 pi. Conductivity of what, guys? Here you need to write conductivity of what? Conductivity of the stainless steel, which is 20. Ks, conductivity of stainless steel into L. So this is what? This is the conduction resistance of the stainless steel. Okay, plus the convection resistance, which is nothing but 1 by HA. So this is H. Area will be what? 2 pi D. Diameter, outer diameter, guys, this is 1.2. So 2 point D into L. 2 pi D into L, guys. So L, easily you can take it common. L को आप common ले पाओगे from this. If you take L common, it will go into the numerator and this L will cancel out, guys. So L is simply going to cancel out. And in this equation, this is known to us. Conductivity of stainless steel is 15. This is also known to us. this is 1000, so everything is known to us. There is only one unknown, and that unknown is TW, the surface temperature of the radioactive waste material. Please check this, guys, the surface temperature of the radioactive waste material. So this TW, this surface temperature you will get, guys, and I hope you are getting some value. So if you solve this, you will get this value close to 370.49. I am writing it here just for your reference so that you will be able to match your answer. So this is TW, guys, we are going to get. Okay, so if he is asking you TW, then the question you will be easily able to answer. But yes, here he has asked you what the central line temperature. Okay, so for finding out the central line temperature, you need to develop some relationship between TO and TW, and that's why if you remember that relationship, then directly you can get the result. Otherwise, you need to use the generalized heat conduction equation. So let me first write the generalized heat conduction equation for the cylindrical coordinates. Okay, so the equation is what? Del 2T by del R square plus 1 by R del 2T del T by del R. So del T by del R plus 1 by R square del 2T by del phi square plus del 2T by del Z square plus Q dot G by K equal to 1 by alpha del T by del T. Okay, so this is the generalized heat conduction equation, guys, in cylindrical coordinate which we are having. But now you need to further simplify. You can simplify this equation. Okay, how? Because here he very clearly mentioned there is no heat transfer in the longitudinal direction, so the heat transfer is in only radial direction. So this will be 0 due to one dimensional heat conduction, 1D, so this will be 0. This will also be 0 again due to one dimensional heat conduction. Due to one dimensional radial heat conduction, this term you can neglect, this term will be also you can neglect, and also there is a steady state, so the temperature is not going to change with time, so this will also be 0 due to steady state. Okay, so the final simplified equation you will get something like this: del 2T by del R square plus 1 by R del T by del R equal to minus Q dot G by K. Okay, you will get this equation. Now if you multiply both side by R, अगर आप दोनों sides को R से multiply कर दें, you will get the equation R del 2T by del R square plus del T by del R equal to minus Q dot G R by K. This equation you will get. Okay, further, you know, this equation you can write it like this: del by del T of R del T by del R equal to minus Q dot G R by K. And I am naming this equation by equation number 1, guys, and I am going to utilize this equation. So guys, for any such kind of problem, first you need to write the generalized heat conduction equation. Here the case is given for the cylinder, that's why I am using generalized heat conduction equation in the cylindrical coordinate. Then we just neglected this term, this due to one dimensional heat conduction, this due to steady state. You will get this equation. Further, if you simplify, you will get the equation del by del T of R del T by del R. Why? Because if you differentiate this, so this will be 1 del R by del R, yes, so this will be del by del R, guys, sorry, so this will be del by del R. Okay, sorry for this, so this will be this. Okay, so del by del R of what? R del T by del R. So if you take this, differentiate this, so keeping this as a same first function as it is, suppose this is first, this is second, first as it is, if you differentiate this, this will be 1, so you will get this term del T by del R. And again, if you keep this same and if you differentiate this, you will get what? R del 2T by del R square. So by solving this, you are going to get this equation only. Okay, and there is a reason why actually I am writing this equation like this. So del by del R of R del T by del R equal to minus Q dot G R by K. So this is equation number 1. Now what you need to do, guys? Let me again write this equation: del by del R of R del T by del R equal to minus Q dot G R by K. Now let us integrate both the side. Integrating both the side. integrating both sides. So if you integrate both the sides, guys, what we get? We will get R del T by del R. R del T by del R, this is equal to minus Q dot G R square by 2K plus C1. This equation you will get. Okay. Now again, if you divide both sides by R, you will get del T by del R. This is equal to minus Q dot G R by 2K plus C1 by R. This is the equation, guys, you are going to get. Let us write this equation by equation number 2. Suppose this is equation number 2. Now if you again integrate this side, this equation, again integrating both the sides, again integrating both sides. So what you will get, guys? You will get the temperature profile. Okay, the temperature profile you will get. Very similar cases are there. You will get T, temperature T, the temperature variation we are going to get, this is equal to minus Q dot G R square by 4K plus C1 ln R plus C2, guys. This is the equation you are going to get, guys. This is the equation you are going to get, and let's name this equation by equation number 3. Okay, so first we simplified that equation, basic equation, generalized heat conduction equation in the cylindrical coordinates, polar coordinates. Then what we did, guys? Then we integrated, we solved that equation just to develop some temperature profile. Temperature T equal to minus Q dot G R square by 4K plus C1 ln R plus C2. Now if you observe this equation, you can easily get the temperature profile by putting the boundary condition. Okay, and what will be the boundary condition? Suppose at R equal to 0, how much is the temperature, guys? At R equal to 0, temperature is what? TO, the center line temperature. Okay, but if you put, suppose because at the center line we assume there is some temperature, there is some finite temperature at the center line, and that finite temperature is TO. We are representing that center line temperature by TO. Okay, at the center. So at the center means at R equal to 0. Okay, so radius we are going to measure from the center only, guys. So radius always we measure from the center. Okay, so this is some radius R. Radius R we are going to measure. Now we are considering this cylindrical element only, guys. This cylindrical element. Okay, so radius at R equal to 0, the temperature will be TO. But here if you check this particular equation, if you put R equal to 0, so this term will be 0. And what will be this term, guys? This term is not defined. Ln of 0 is not defined, guys. And here if you check R equal to 0, so this will be 0 and this becomes infinite. It means the del T by del R becomes infinite at R equal to 0. That is not possible. Okay, so this is also not the case. So del T by del R cannot be infinite. And here if you put R equal to 0, then temperature is also you will not be able to define. What it means? It means what idea we are getting? It means the C1 is required to be 0, guys. Otherwise there will be some mathematical difficulty. So because at this R equal to 0, you will not be able to define this. What it means? It means this term is 0. So this term is 0, guys. This term is 0. Not this term actually. The C1 is 0 actually. Okay. So what you can conclude? Keeping that thing in mind, guys, if you put R equal to 0, you will not be able to define this. Okay. And that's why C1 is 0. This is 0. So this entire term you will be able to remove. Fine. So what you will get the final equation, guys? You will get del T by del R. If C1 is 0, del T by del R equal to minus Q dot G R by 2K. This is the equation. This is the one equation. Let's name this as equation number 4. And if you put here also C1 0, you will get temperature T equal to minus Q dot G R square by 4K plus C2. And let's name this as equation number 5, guys. And these are two very important equations. Okay. Now you can apply the boundary condition. So if you check it here, at R equal to 0, the del T by del R also becomes 0, guys. Del T by del R also becomes 0. What it means? It means temperature equal to T max and this is equal to TO at R equal to 0. So at R equal to 0, the temperature which is there, that is a maximum temperature. Okay, and the profile, the temperature is going to vary inside the material, inside the radioactive material in a parabolic manner. Okay, something like this. So something like this. So let me make it some more symmetric so that we will get. Okay, so let me make it something like this. So something like this. So something like this. So here the temperature is TW, here the temperature is TW, and the central line temperature is what, TO, and the temperature is going to vary parabolically. Inside the material it is going to vary parabolically. Okay, so because that idea we are getting by observing this equation, the profile of the temperature is parabolic. Okay, but yes, you can further put it here in this equation. In this equation, if you put R equal to 0, so the temperature T equal to TO, yes or no? At R equal to 0, temperature equal to TO. So if you put it like this will be 0, this will be 0, and this will be TO. What it means? It means C2 equal to TO, guys. C2 equal to TO. This you are going to get. This is another important result. At R equal to 0, the temperature is maximum. At R equal to 0, the temperature is TO. That's why the C2 is equal to TO. Now if you put the value of C2 by replacing it by TO, you will get the relationship between T and TO. So T equal to minus Q dot G into R square by 4K plus C2, and C2 is nothing but TO. So this is the equation, guys, which we want. Okay, this is the equation. You can remember this directly also, but just to show you the proof, that's why I just derived this equation in front of you. So T equal to minus Q dot G R square by 4K plus C2, and C2 is equal to TO. Okay, so further if you take this side, and if you take minus common from both the sides, you will get TO minus T, that is equal to Q dot G R square by 4K. So you can write this equation something like this also. Okay, now what we want, guys? We want central line temperature. हमें ये चाहिए. We want this central line temperature. So TO equal to what? Suppose if you will put this R equal to capital R. R equal to capital R means what? At R equal to capital R, T equal to TW. Yes or no, guys? So R is the representation of radius which we are taking from the center. So R, if you take R equal to capital R, means this is the capital R, suppose this is capital R. So at R equal to 0, temperature is TO at the center line. But when R equal to what? Capital R, means this radius of the radioactive waste material, which is nothing but 0.5. Are you getting idea? So just by this small r, we are just representing the radius, the distance from the central axis. So r is just a representation of distance from the central axis. R is 0 at the center, and r is equal to capital R, which is equal to 0.5 at the surface. And at the surface, the temperature is TW. Okay, so this is another boundary condition at r equal to r, which is nothing but 0.5 meter. Okay, the temperature is TW. So if you put this here, you will get TO equal to TW plus Q dot G R square by 4K. Guys, this K is the conductivity of what? The stainless steel or radioactive waste material? This K is the conductivity of the radioactive waste material, guys. Okay, now you can put all the values and you can enjoy the answer. TO equal to TW, I think we obtained this TW. This is 370.49. 370.49 plus Q dot G, which is 2 into 10 to the power 5. Okay, volumetric heat generation, R square 0.5 square divided by 4 into K. K is nothing but 20. Okay, just solve this, you will get the answer, guys. Okay, I hope you will get some answer by solving this equation. Please try, and then I will put here the answer in front of you, guys. Fine, just try it here. The central line temperature you will get by solving this equation, guys. Okay, let me check here for some calculator, otherwise you can check it here, guys. You will get this temperature will come out in degrees Celsius only, guys. This will come out in degrees Celsius. Okay, and if you solve this, you will get answer 995.49. okay, this will come out 995.49 degree Celsius. But he asked you the answer in degree Kelvin. If you check all the given options, guys, here, all the given option, he has given you the answer in this, and all answers are in Kelvin, guys. So obviously you need to convert this answer, degree Celsius, into Kelvin by adding 273.15. So if you add 273.15, you will get the answer, which will come out close to 1268 Kelvin. 1268 Kelvin. Okay, so 1268 Kelvin is the answer, center line temperature for this question. I hope this is very much clear, guys. You got the basic idea to get the result, even because in GATE sometime, because there are so many subjects, there are so many formulas, and it is difficult to remember all those formulas. So basic steps, basic idea you need to have, how to derive the formula, how to get the formula, and it is not going to take much time, guys, because here I discussed with you the entire process. That's why it has taken much time. Otherwise, if you are solving this question, you are writing the generalized equation, you are solving it, removing all those terms by going with all the assumptions, you will get the answer very easily in a time of 3-4 minutes. That much time this question is going to take. So you can plan to solve this question at the end if you get the sufficient time. So in GATE, different kind of question you will get. Some very direct question which you will be easily able to solve in 20-30 seconds, so you can go for such kind of question, okay, in the beginning only. There are some question you will be able to solve in 1 minute only, that also you can try in the beginning only. But there are some question which are going to take the time. Even if you know, okay, yes, I am very much strong, comfortable in those solving those kind of question, then also it's my suggestion to you, try to solve such kind of question at the end only, because in the first 1.5 hours is very important, because in that time period you are going to get the confidence. Yes, I attempted a good part of the paper, I attempted more than 70-80%, okay, and then the remaining part, 20-30%, whatever is remaining, and the difficult part which you feel is going to take much time, that you can think of in the last 1 hour or last half hour, means last half time. Okay, so see, in that manner you need to focus. Yes, in heat transfer there are some questions which are very easy actually to solve, but yes, lengthy one, okay, comparatively lengthy one. Okay, so I hope this question is very clear, guys, and you got the idea. And again we will meet, we'll solve some more similar kind of question. Thank you, keep preparing, and best of luck for your examination. Good luck.